Okay. Any questions? Mm-hmm. Right, but for every y there must be a unique x. You cannot have a one value that came from different x values. So, okay, so for example, if I look at this function, right? Well, actually, let me use function notation. If I do f of -2, that's -2 squared equals 4, right? -2 is the number in the domain, that's the x value. 4 is the number in the range, that's the y value, right? But at the same time, if I compute f of 2, that's 2 squared, that still equals 4. So that's what I'm saying. You have a single y value corresponding to two different x values. So if we do that kind of a blob blob type of thing, that's what just happened. You had two different points. Yeah. So that's still a function, but it's not a one-to-one function. Okay, so we don't want this to happen. So the functions that don't do that are called one-to-one. So that's what I wrote. That's what that meant. If x1 is different from x2, then the values of the function will also be different. What this implies, you cannot have different x's but same y's. That is one-to-one. That is the definition. If your x values are different, then the y values will be different for no matter what two x values you look at. Not the case here, right? -2 is different from 2, but 4 equals 4, so that contradicts that definition. So x cubed, okay? If I consider this, f of x equals x cubed. For every x, you're going to get a y, and if you take any two different x values and you cube them, you're going to end up with two different y values. Okay? So that's basically what. But really, all you need to get from there is how to, just do a quick graph or something like that. And if it passes the horizontal line test, then it's one-to-one. That's really the big thing. We're not going to get all down and dirty with actually figuring out whether the function is one-to-one or not. Because again, we need one-to-oneness to find an inverse. Okay? And it's really going to kick in, well, what we're going to talk about today. We're going to talk about a new family of functions, and then we'll realize, oh, that looks like one-to-one type of family. And we'll be able to find the inverses and so forth, because it'll get us to solving equations. We didn't really need any of that inverse theory before. We will find solving equations without inverses. Won't be the case after today, when we get this new family of functions. But basically, again, that's what it means that you don't want to have two ordered pairs that share the same y value, basically. That's what it is. Okay? So that's, there are many definitions. There's one. There's another definition saying if the y values are the same, then the x values had to be the same as well. That's also a definition of one-to-one. So if you have 2 points that have the same y value, then they will have the same x value. So you're looking at the same point, basically. That's what it says. Okay, so that would be a one-to-one function as well. Right, so the x squared is not, right. That's not one-to-one. And if you think about the graph, it's a parabola, clearly fails the horizontal line test. And in the end of Monday, we were doing that whole restricting the domain thing to make it one-to-one, kind of cutting half of it. So we wanted a piece of a function that still spans the entire range, but stays one-to-one. Okay? Yeah, we're going to learn about E today. E, it's a new number. Yeah, number E. Is that fun? Why not? Well, you only have one number that has a letter attached to it, right? Well, it's not really a number. It's okay, two numbers. I and what else? Pi. Well, after today you're gonna have another one, E. Oh well, just a number. That's all. I mean, you can. I have a book at home. A student gave it to me. It's about A thick. It's about 500 pages, and the title of the book is Mathematical Constants. And there are a whole bunch of constants. Each one of them has a name, like a letter. So yeah, you only have getting one today, and it's one of the big ones. And that book actually had that one misprinted, so that kind of sucked. You cannot make an error in one of those fundamental mathematical constants. But yes, we will learn about E today. But first, I'll tell you, it's kind of a legend, or maybe I don't know, story. It's kind of fun. I don't know when it happened, a long time ago, somewhere in Middle East, because, everything we study came from there, algebra and all that. So this, what do you call those guys? The guy, he just made a really beautiful chessboard with chess figures and stuff like that. It was kind of cool. So whatever the king or whoever was ruling the world at that time was like, oh, I kind of like that. Why don't you give it to me? I'll pay you whatever you like. And the guy's like, well, why don't you put one grain of rice on the first square and then double on the second square and then double on the third square? Just keep doubling the number of, grains of rice. And the king was like, oh, that sounds relatively cheap. You got yourself a deal. Have you heard that story? All right. Well, anybody plays chess? What size is that board? Well, how many squares do you have? 8, right? 8 by 8. So you have 1, 2. Okay, let me try it again. One, 2, 3, 4, 5, 6, 7, 8. Right? Is that 8? 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. So that's a chessboard. Is that okay? So what the plan? You're going to put 1 over here, then you're going to put how many over here? Keep doubling. 2, and then 4. So what you're doing, you just keep raising 2 to power, right? 1 is 2 to the power 0, 2 is 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, right? 2 to the power 5, 2 to the power 6, 2 to the power 7. So what is it? 32, 64, 128, 256, right? 512, 1024, right? It's getting out of hand, right? 2048. And we're halfway through the second row. The last square here will contain 2 to the power 63 grains of rice. Okay? If I actually compute that, yeah. Okay, what is that? So that's 3, so that's 1,000, million, billion, trillion. Did we have that discussion? What's after trillion? Quadrillion, and then that thing after that, and then 9 of those. And that's just on one square. The one before had 2 to the power 62. So, still. And you add them all up. And I think you end up with something like, more than grains of sand on Earth type of thing, or matter in the universe type of kind of numbers. So yeah, but this would be an example of an exponential function. So what you're keeping 2 the same, all you're changing is the exponent. So the variable is in the exponent now. And the thing about these functions, they grow really, really, really fast. So you might have heard the term Oh, it grows exponentially. So that means just takes off. It grows really fast. It's kind of nice at the beginning, but it gets out of hand really, really fast. And they were trying to do that, so at some point they filled the entire castle with rice, and I don't know. So yeah, I don't know the rest of the story. You can Google it. It's kind of, I should have done it before class. But anyway, so exponential functions. That's what we're going to start looking at today. They grow really, really fast. So that's section 5.2. So a definition of an exponential function is f of x equals a to the power x. So a is a constant, x is a variable. So a is a real number. So a is a constant. Now another thing, a is strictly positive. And also a is not equal to 1. So there are kind of many conditions on a, but basically all it is, it's a positive number not equal to 1. Because if a equals 1, it's a very boring function. 1 to any power is 1. So we don't consider that. It's just, you just get 1. Now a little bit of verbiage. A, we call that a base, so that's a base. X is an exponent. So for example, what we just played with was a function 2 to the power x. And actually, the domain of this function is all real numbers. You can take 2 and raise it to any power that you like. Okay, it could be positive, negative, fraction, irrational. I can do 2 to any powers. You know, if I do 2 to the power 5, it will give me the answer. If I do 2 to the power negative 4, it will give me the answer. Oh, I did divide? Yeah. 2 to the power negative 4. Yeah, that's better. So it gives me the answer. I can do 2 to the power pi. If I wanted to, it will give me some value. Okay? So x is anything. So the domain of this function will be all real numbers in general. But let's try to graph this thing. So every time when we're just starting new functions, the only thing we can do is to, well, make a little table of values and come up with a bunch of points and plot them and see what that gives me. I'm going to take a few negative numbers, 0, and a few positive numbers. Okay? So now remember what negative exponents do. If I look at 2 to the power negative 3, do you remember what negative exponents do? What is the interpretation of a negative powers? Yeah, I remember teaching you that. No. Yeah, it's a reciprocal. It's 1 over 2 cubed. That's what negative exponents. So it's 1 over 8. Okay? So 2 to the negative third is 1 over 8. To the negative second is 1 over 4. To the negative first is 1/2. So negative exponents are reciprocals. What is 2 to the power 0? 1. So anything to the power 0 equals 1, except for 0 itself. We cannot do 0 to the power 0. And then the rest is simple, 2, 4, 8. Okay? Now, a nice thing about these functions, no matter what the exponent is, the y value will never be negative. It actually won't be 0. I can get as close as I like to 0 by taking 2 to some big negative numbers, 2 to the negative 20. It's going to be very small, but still positive number. So that's something like 1 over 2 to the 20. That's huge. In the denominator, if I do this, it's 2 to the power 20, it's that. But 1 over, so if I take the reciprocal, so it's a very small but still positive number. And that will happen. It will never go below the x-axis. It will never actually hit the x-axis. I can get as close as I like to the x-axis, but I will never touch it. So that looks like an asymptote of sorts. These functions have a horizontal asymptote at the x-axis. But anyways, we'll talk about this in a little bit. But if I plot all these points, let me get rid of this. If I actually plot these points, I'll get 0, 1, 1, 2, 2, 4, 3, 8. Well, 8 here. And then on the other side, I have negative 1, 1/2, negative 2, 1/4, negative 3, 1/8. So I'm getting really, really close to the x-axis on this end, but then I'm flying off on that other end. So I have this function that really starts going up really rapidly while it's getting really, really close to the x-axis on this end, but it will never touch. So the x-axis really plays the role of a horizontal asymptote just on the left side. Okay, you don't have a horizontal asymptote on that side, but on the left, you do get one. Is that okay? Isn't that a friendly graph? Would that be a one-to-one function just by looking at this graph? Yeah? Why? Because it passes the horizontal line test. Good. Good? All right. Well, let me try one more function. F of x equals 1/2 to the power x. So I'll do it the same way. I'll build a table of values, x and 1/2 to the x, and I'll just plug in a whole bunch of values. Negative 3, negative 2, negative 1, 0, 1, 2, 3. Okay? So I'll do the easy ones first. If I take 1/2 to the power 0, we'll get 1. If I'll take 1/2 to the power 1, I'll get 1/2. If I'll take 1/2 to the power 2, I'll get 1/4. And if I take 1/2 to the power 3, I'll get 1/8. Right? While on the other side, if I take 1/2 to the power negative 3. So we know negative means reciprocal. So I'll have to take a reciprocal of 1/2, which is just 2. So it's 2 cubed. So that gives me 8. If I take 1/2 to the power negative 2, that's the same as 2 to the power 2. So that gives me 4. Is that okay? So negatives just take reciprocal. So I'll get those points. Right? Now, if I plot them, and I'll plot them on the same set of x's, I'll have this point here, this point there, this point there, this point there. So what does that look like? Well, close enough, right? Do you see the relationship between these two graphs? What is the relationship? Well, no. They're flipped, right? Over what? Y-axis. Now, go back when we studied all those transformations and translations, when we were moving graphs around and flipping them. when do you flip a graph around the y-axis? Where? Because remember, you can put a negative all the way up front, or you can put a negative on the inside. On the inside, right? Was that a guess? Yeah, it sounded like a guess. But remember, if you put a negative on the inside, that means you change the sign of your x value. And that's, if you take your, positive 2, turn it into negative 2, the graph flips over the y-axis. So yes, looks like that flip occurs. And we remember from chapter probably 2, that we, or maybe 3, then we flip around the y-axis when we put a negative on the inside. Right? So it's a graph of f of negative x. But check this out. If my f of x equals 2 to the x, well, what is f of negative x? It's 2 to the negative x, right? And we just talked about negative exponents. Negative exponents mean reciprocals. So 2 to the negative x is the same as 1/2 to the x. So that's consistent with that part in our book when we were flipping graphs. And actually, the rest of the transformations still apply. If I go 2 to the power x plus 4, that means I will shift the graph of 2 to the x 4 units upward. Remember that? If I do 2 to the power x minus 1 like that, that means I'll shift the entire graph 1 unit. Where? Left or right? Right. So all those things still apply, all those transformations. Okay, so in general, an exponential function has the following graph. All the graphs of the exponential function would either look like that. They're all passed through the point 0, 1. So this would be the case where the base is greater than 1. So the function will be growing. Okay? The bigger the a, the steeper the function. Or if a is less than 1, the graph of the function will be flipped over the y. So this is the case where a is positive but less than 1. What? Yeah, because you get some number to the power 0, so it's always going to give you 1. That regardless of what the base is. Whether it's 10 to the power x or whatever, you're still going to hit it at 1. Now, for both of those graphs, we can answer the following questions. The domain is just all real numbers. You can use any values for x to plug them in. Now, what about the range? What is the range of these functions? Just by looking at the graph. Range? What? Just, yeah. Positive numbers, so from 0 to infinity, not including 0. It will never hit the x-axis. Actually has a horizontal asymptote, y equals 0. So the x-axis is a horizontal asymptote, either on the left or on the right, depending on what kind of function you look at. And the big thing that we'll also notice is that these are one-to-one functions, right? So regardless of the base, exponential functions are one-to-one. Is that okay? So far, so good? All right. Now, if I go back to my 2 to the x graph, now I'll make up a new one. So remember we just did that 2 to the power x graph, and it had the following points. I'll try to be very careful. 0, 1, 1, 2, 2, 4, right? And then 3, okay. well, not that careful. 3/8-ish. On this end, -1 gave you 1/2, -2 gave you 1/4, and -3 gave us an 1/8. So something like that, right? So when I connect them, the graph looks like this. So this was 2 to the x. Now I want to do 3 to the x. It will still look the same. It will go up on the right, it will go down on the left, because 3 is greater than 1. But it will be a lot steeper on the right, because if I plug the positive numbers, we're getting 1, 3, 9, 27. Right? If I be raising 3 to those powers, so look what happens. It still goes through 0, 1, but then 1, 3, 2, well, 9, I'm already off the board. So it will be much steeper on this end, while it will be closer to the x-axis on the other end, because if I go negative powers, I'll get 1/3, 1/9, 1/27. So I'm just taking reciprocals of those other numbers. So actually it's going to be less than 1/2, less than 1/4. So it looks like that on. So it's below on the left, but above on the right. So this was 3 to the x. Okay? Yeah. So the bigger the x, so like 10 to the x will look something like that. Okay? While, you know, something like 1.1 to the x will look like that, and this will be 10 to the x. Okay? Are you buying that? I shouldn't be hitting the x. I mean, I probably should have used that full plot thingy to get better graphs. But that's the idea. The steeper the base, the bigger the base, the steeper the graph, the smaller the base. Because, right, we cannot be, remember, the base cannot equal 1, then you're just going to flat line like that. It's just always 1. But if it's slightly bigger than 1, it will still fly to infinity. Okay, any base, like something really small, like 1.01, it's a very small base. And if I start doing those powers like 63, you know, it's 1.8, not that dramatic, right? But 63 is still a small number. If I do 1.01 to the power 100, you know, it's 2.7, but it's still growing, right? 1.01 to the power, I don't know, 2500. All right, so I'm flying off now. Okay, it will still go to infinity. Is that okay? So let's try this. Sketch the graph. Okay? Now, all those transformations that we studied earlier still apply. How many students do I have left in this class? 9 today. I know, that's what I told you, just sign up. Who else is there usually? You know, that kid? Yeah, 2. Yeah, so we still have about 15 students. So now remember, we know the graph of 3 to the x, right? What this -1 right here is going to do to the graph of 3 to the x? No, you're just subtracting 1 from x, it's going to shift it to the right. It's going to shift it 1 unit to the right. I'm not multiplying it by negative, I'm just subtracting 1. So this is subtracting 1 from the x, so it shifts it to the right. What about that +2 on the outside? Goes up 2. Now, the big thing here you have to realize, since the original graph had a horizontal asymptote at 0, now you're shifting everything up 2 units, you got to take the asymptote with you. Okay? So the graph of this function will actually going to shift 2 units up So it will have a horizontal asymptote here. Okay? Well, but remember, the original graph had a horizontal asymptote at 0. Right? So now if you shift everything to units, it's going to, because the common mistake would be you shift it to units, but then you still approach the x-axis. That will be wrong. So it will be evening out here. Now let me show you this. So this would be the graph of just 3 to the x plus 2. I didn't shift it 1 unit to the right yet. So it's going to pass through 0, 3 now if you push everything 2 units upward, right? But now you have to move it 1 unit to the right. I can actually do that like this. Right? It will have a different x-intercept now. This x-intercept is something else. Okay? We can actually find that. I'm sorry, did I say x-intercept? I meant y-intercept. We can still find that y-intercept, because to find y-intercept, you put 0 for the x, right? The y-intercept, let x equal 0, so you'll get 3 to the power 0 minus 1 plus 2, right? So that's 3 to the negative first power plus 2, so that's 1/3 plus 2, so that's 2 1/3. So that's that point. It's not really drawn to scale, but this is 2 1/3. So everything went up and shifted to the right. Is that okay? So, what? That looks like 1/9? No, that's a 3. Well, I cannot make those precise drawings on this board. But all your old theories of graphing still apply. To find the y-intercept, you set x equal to 0. You add number to a function, you go up. You subtract number from a function, you go down. You add number to a variable, you go to the left. You subtract number from the variable, you go to the right. So all those things still apply. Okay? So we can play with those graphs. I can ask you to sketch the graph f of x equals negative 2 to the power x plus 1. I'm just saying, that's enough. Negative 2 to the power x plus 1. Shifts left 1 unit, and what is the negative in front going to do? So everything is negative now. So it flips it over the x, right? So you're making all positive numbers become negative numbers. So if I grab this, so remember, this was the original graph, right? Now if I shift it 1 unit to the left, I can find that x-intercept. I'm sorry, y-intercept. If I put 0 for the x, I'm just going to be left with 2 to the power 1, right? So actually it shifts here. But then if you flip it, it will look like that. So it goes through negative 2 now. But it still has a horizontal asymptote at the x-axis because we haven't moved up or down. We just flipped.
So in order to figure out like how you have to shift it left or right, you have to find like y.
That will help because that's easy to do, right? You just plug in 0. Okay? If I do this example, let's say f of x equals 3 to the power x minus 2, like that, okay? It's easy to find the y-intercept still. What would be the y-intercept? Well, negative 1, because if you put 0 for x, you get 1 minus 2. So, your original graph went through 0, 1. Well, you moved it down 2 units. So instead of going through 1, it's going to go through negative 1, right? Where will be the horizontal asymptote? At negative 2, right? So this will be the horizontal asymptote. So the graph looks like that. But this x-intercept will be very hard to find for us, okay? Because how do we find x-intercept? You said y equal to 0, right? To find x-intercept, set y equal to 0. So we'll be left with 3 to the x minus 2 equals 0. Well, that's an exponential equation. We don't know how to solve those yet. Okay? It actually won't be anything pretty. It'll be a pretty nasty number. But for the y-intercept, that's simple. You just set x equal to 0 and you'll get it. Or here you didn't have to do that. If you realize that everything shifts 2 units down, positive 1 will become negative 1. Okay? All right, so all those things still apply. I mean, it should still look kind of the same as the previous one. So any questions on the graphing? Now, when you're going to be doing your homework or the quizzes on this stuff, that's section 5.2, it will actually be challenging to graph these things. Let me show you what it will look like. Because it's really hard to find those points. So the computer will actually ask you, okay, so what is your base? And you have to say, well, in this case, the base was, what was the base, 2? Or 3, whatever. And then you'll say, okay, then I'm going to flip it over this axis or flip it over that axis. I'm going to shift it 2 units up. I'm going to shift it 3 units left. Or maybe I'll even stretch it or not, because if there's a constant, you'll have to stretch it. I'm just going to open, oops, I'm going to open an assignment, show you what it looks like. So let's see, homework, let's try it on the homework. All right, so inverse, that's easy. Okay, whatever. Wow, I'm spending a lot of time on inverses here. Okay. All right, well, that's not. Well, is that what you want? Yeah, we'll do that in a second. But you know, things like that, it should be pretty straightforward, right? It's 3 to the x, so that's exponential. It's flipped over what axis? If it's negative all the way up front. And then minus 3, it went down 3 units, right? So now if you look at these graphs, which one of them is flipped and just went down 3 units? A, right? So, yeah. 26? So, yeah, 26. All right? So how would we do that one? It's 2 to the x, right? And where we're going to shift it when it's x plus 5. So shift the graph 5 units up, shift the graph 5 units left, right? So B in this case, right? Doesn't. Oh, yeah, I have to put 2 in there. Okay, shut up. Oh, now we have to graph it too, right? So here's the graph. So that's an exponential. Wow. So what's our y-intercept? Okay, well, yeah, this is better. Yeah, this is what I was talking about. This is going to cause us problems. So base is 2, right? Now, vertical stretch, horizontal stretch, we don't have to worry about that, because remember, that happens if you put a coefficient in front of everything. If you multiplying your function, that's when stretches happen. So nothing happens there. So what's going on here? Vertical shift, that's up or down. Don't do that. Horizontal shift, 5 units to the left, right? Reflect over the x, reflect over the y? No. Excellent. Let's see if there's another one like that. I'll teach you E in a minute. You're not ready for E. Yeah, I know. I'll teach you E in a second. Just slow down there. So what's going on here? Select the correct choices. Refract the graph of, so the base is 2, right? Look at that. We have a negative in front of 2 and a negative for the power, so we're going to reflect it over the x and over the y, right? And this is positive 5. So we're just adding 5 to the graph. Where's that going to go? So you see across the y-axis, then across the x, and then shift 5 units up. So it looks like this would be, oops, the good option. Right, negative, again, remember your base is always positive. By the definition, you cannot have, if it had the parenthesis around negative, then yes. But then our function would get completely crazy, because with negative base, the domain would be really bad. All right, let's see exponential tool. So same thing. Base would be 2, right? Reflect over the x, reflect over the y, right? Vertical shift, 5. Horizontal shift, no, and none of that stuff. Because of the negative in front of the x. Okay, so it's negative where the variable is, that's because that's multiplying. So here's another one. So what will happen here? You shift 2 units to the right, 1 unit up, but then whole times 5 thing, that's your stretch. Okay, so that's the vertical stretch by 5. So again, you'll start with the exponential tool, and then let's see. So the base is 2. We're going to shift vertically by 1, right? We're going to shade horizontally by 2, right? And then this whole 5 will vertical stretch. Well, you're going 10. Yeah. Uh-huh. So is that right? No. No. Order of operation, you do the powers before you multiply. So 5 times 2 to the x is different from 10 to the x. Is that what you're saying? Well, but different. The one just multiplies everything by 5. The other one just, well, let me show you on this thing. Ah, well, that's all right. What was that full plot? Yeah. Well, let me show you. If I do 2 to the power x, okay, and then I'll do 10 to the power x, and then I'll do 5 times 2 to the power x, okay? So you see what happened there? When you just multiplied by 5, your x-intercept went all the way. I'm sorry, why do I keep calling it x-intercept? Your y-intercept got multiplied by 5 as well. It was 1, now it's 5. While 10 to the x is different, right? 10 to the x still goes through 0 to 1. And you see 10 to the x will outperform 5 times 2 to the x eventually. See that? It goes up much stiffer. No, that's a good question, but that's about the order of operation. You do the powers before you multiply. So anyway, so you're going to have fun with the way my math lab is doing this thing. Okay, good. So let's take a little break. And some more. What? Oh, I know we missed that in this classroom. Uh, all right, so let's talk about interest, computing interest, investing. What? This is this is interesting, right? What? Don't you want to know how they compute your payments on your whatever student slash car slash maybe house in a future loan? You know that the reason for our economical collapse because people didn't know how to compute the interest. True story.
No, it's because people are dumb and they said things they couldn't.
No. See, but they do know how to compute the future, when your interest gets adjusted by whatever, things get scary. But anyways, we've dealt with one form of interest called simple interest. And that's I equals PRT. We've dealt with that. Remember that? I was the interest. P was the principal. Yeah, there is a difficult interest. There is really difficult interest. Principal. So what is that? Is that a principal or principal? Which pla? Principal? Principal is a pal, right? Okay. I can never tell. R is the rate, and T was the time. Okay? So, for example, if we invest $1,000 at, I don't know, 3.5 rate for 10 years, at the end of 10 years, we'll have, a little bit more, right? At the end of 10 years, we're going to have the original investment plus the interest, right? So it is 1,000 plus 1,000 times the rate, which is 0.035 times 10. If we just do the simple interest. Well, again, this just tells you the interest. You still have $1,000, right? Plus whatever the interest you're going to make. Right? You shouldn't be less than $1,000. But anyway, so if we compute that, that looks like what? 350. So it's $1,350. Is that right? So that's simple interest. Now, usually it doesn't happen like that. You don't just, well, this means that, what is it, 10 years, so that's 360, no, 3,650, maybe 2 days, right? So that means that one day before it hits 10 years, you still have only $1,000 in your account. And then all of a sudden you get this, boom, 350. Okay? That doesn't happen like that. They usually compute the interest on few occasions while you get to those 10 years span. Does that make sense? Sometimes they do it at the end of every year. Sometimes they compute the interest at the end of every month. They can do it at the end of every week, at the end of every day, every hour, every minute, every second. Just depending on whatever the thing you just signed. Okay? So it's not simple interest. We call it compound interest. So that's the new formula, compound interest. Compounded, or maybe interest. Or maybe, I don't know. Sometimes called compound, sometimes compounded. I don't know. Depending on whichever you book, who cares? Compound interest. So the formula for that, A equals P times 1 plus r over n to the power nt. Yeah, so the formula got a little fancy. Now this formula takes into account your original investment. You do not have to add it to your interest. It doesn't just compute the interest, it computes the whole amount. Okay, so A is the amount, which is the principal plus interest. So we don't have to add that anymore. P is the principal. R is the rate. T is the time. And N is the number of times that interest is being compounded. So if it says the interest is compounded, weekly, then it's 52 times per year. If it says the interest being compounded monthly, it's 12 times per year, and so forth. So number of times the interest is computed per year. Or compounded, it's the same thing. Don't challenge me on the verbiage. Okay? So if I do the same problem, invest $1,000 at 3.5 rate for 10 years, but the interest is being compounded at the end of each year. So compounded annually. Well, computed. Basically what they do, you have $1,000 in your account for the whole year. Okay, that's what they're going to do. So you're starting. So year one, you started with $1,000, right? At the end of year one, this is the end of year one. They went ahead and they computed the interest. So they just 3.5% for that first year. So the interest, and they do it at using the simple formula, just simple interest. At the end of the year, it's just $35 because it's 3.5%. So then total that you have is $1,035. So the second year, you're going to start with $1,035. And then at the end of the year, they'll compute 3.5% of that amount. Yeah. So it's growing. Right. Yeah, so look at the difference. When I compute just 3.5% of that amount, it's $36.22-ish cents. So that's extra $1.20 that we make versus just the simple interest. Yeah, so we'll take that amount, so it's 36.225, and we'll keep that decimal, because that adds up. Not going to be rounding. Added to that, so technically we have 1,071,225. Well, yeah, especially on your debt. Now on your investment, could be simple because it's slower, but on your debt, they'll compound it. I mean, if you look at your credit card statement, it will actually say in the very fine print how they're going to compound the interest. They're going to say, get simple interest like on a weekly basis, so every week. So that means it's compounded weekly. Okay? You can actually challenge them and compute it and call them up and say, hey, what gives? Because I just cracked my numbers and you computed my interest wrong. No, because that is really, because it's really weird because they have to, because your balance changes almost. If you use your card frequently, it could change a few times per day. So they look at your average daily balance and then they compute the interest off of that. Kind of weird. Anyways, but so that's what you start with on the third year. And then you compute 3.5% of that. So if you compute 3.5% of that, so you made a little bit more, $37.50. Right? Instead of just making 35 each year you're making a little bit more. So they take that interest, they add it to your principal, so your money grows a little faster, right? But instead of doing this process over and over and over again, I can just use my compound interest formula. If I just plug all those numbers in, it will just tell me what I'm going to end up with at the end of the year 10. Well, so it's going to be 12 times a year. It's really hard to do it by hand. Then the interest is going to be compounded 120 times in the life of that 10-year investment. Yeah, at the end of each month, they're going to compute not 3.5%, but 3.5 divided by 12, so that's the percent per month. That's what this is. This is your rate divided by number of times. Okay, but if I do it annually, let me just show you with this formula. So in the formula, A equals P times 1 plus R over N to the power Tn. And if I say it's annually, that implies that N equals 1. We only compound interest once per year. Okay? So then it'll just be A equals 1,000 times 1 plus 0.035 over 1 to the power 10 times 1. Okay? So it's 1,000 times 1.035 to the power 10. That's what we're going to have in our account at the end of the 10th year. So if I just plug it in my calculator, 1.035 to the power 10 is that times 1,000. So $1,410 and about 60 cents in 10 years. Now, compared to the simple, when we did the same thing with the simple interest, we only got 1,350. Now we got 1,410, so it's extra $60, just because they changed how they compute the interest. See that? If I do the same thing only monthly, so same scenario, but compounded monthly, so that means N equals 12. So it's 12 times per year. So at the end of the first month, you compute whatever the 12th of your interest is. But I'm not even going to bother doing this by hand because that's 120 computations. Okay? Now with Excel, it's easy. You can just copy. But without Excel, that's a lot of, calculator. I mean, it's going to take you what? Maybe it will take you an hour, roughly speaking, right? If I tell you, it's about 30 seconds per line, so it's 60 minutes. It'll take you an hour. But if I do this in the formula, so it's 1,001 plus 0.3, okay, 0.035 over 12 to the power 12 times 10, right? Because N appears twice in our formula. It's in the denominator, and it's in the exponent as well. Okay? So it's 1,000, 1 plus whatever this is, that's 35, to the power 120. So if I use the calculator, I'll do it this way. I'll compute 0.035 divided by 12, so whatever that is, plus 1. So I just computed whatever's inside the parentheses. And then I'm going to raise it to the power 120, so that's that. And then times 1,000. Still bigger, not by much. Didn't have that dramatic jump, not $60, but it's extra $8 or so, right? So it's 1418. What were the decimals? 34. Does that make sense? So now, like if I keep changing that number N, if I keep changing the number of times the interest is being computed, it will change the final amount. But see what happens. Let's say if instead of doing it, we did it, what, monthly? We can do it weekly, right? Let's do it daily. Now, when we do it compounded daily, it's 365 per day. You ignore the whole leap year business. We're not going to get that precise. In reality, they'll take care of that extra day. But for 10 years, right? Because in 10 years, what? Yeah, but again, in a span of 10 years, how many leap years can you have? Yeah, you can have 2, right? You can have 3. You cannot have 4. Right? Okay, so let's just 365. I know, it's fine, but let's just assume, for the sake of you doing these problems and for the sake of my math lab checking your answers, it's 365. We're not going to be doing that. So again, if I do the same thing, it's 1,000. That's the future amount. 1 plus 0.035 over 365 to the power 365 times 10. Okay? So that will tell me how much money we'll have in my account at the end of the year 10 if we compute that interest every day. Now, daily interest is really small. It's 0.035 divided by 365. That's the interest per day. That means 5 decimal places, that e to the power 5, so it's a very small number, plus 1, so that's that. You see 4 zeros. And then, bless you, raise it to the power, that's 3,650, right? 365 times 10, so gives you that. You made extra 70 cents. Look at that. Well, the difference between compounded monthly, we had 1418.34. This is 1419.04, so it's extra 70. Yearly was 1410. So yeah, you see the numbers are still growing, but what? What do you notice? It's slowing down, right? So I'm not going to get into 04. I'm not going to get into all the details, but again, it will be a shape of your exponential function. Remember, exponential functions, they do have this slowing down bit. So if we actually try to graph these things, we're going to be looking at the whole slow down part. Okay. Yeah, so it will still increase, but very slightly. And I can do it, instead of daily, we can do it hourly. We can do it every minute. We can do it every second. Let's do it every second while we're at it. Oh, we'll compute in a minute. Compounded every second. So it's 365 days times 24 hours times 60 minutes in the hour times 66 seconds in a minute. So that's how many I got. You got minutes. Looks like you got minutes. Yeah? So whatever that number is, what is that? 31,536 seconds in a year. Okay, so N, I'll just do this. Okay. We might not even, we'll notice the increase, but it won't be that dramatic. So it's 1,000, 1 plus 0.035 over this crazy number. Plug that in my calculator, so this. So what is the power? 3, 1, 5, 3, 6, 0, 0, 0 times 10, another 0. Bam. So yeah, we made what? 4 changed into 6. We made 2 cents extra. Right? Or maybe 3 cents. So it's still higher, but not by much. And it will keep increasing. The change will start happening down the road over there, which we don't really care. Okay? So at some point, we'll just say, because we can actually talk about the interest that is compounded continuously, meaning every instant of every instant of every instant. So constantly, just while I'm saying this phrase, they compounded an interest billions and billions of times, just infinitely many times. Okay, and it will make a slight increase. Let me show you. I'm going to teach you later how to compute that, but 0.035 times 10. So yeah, this is the absolutely highest number that we can get out of that investment without changing anything else. So it's basically the same as what we got from every second. Okay, if we do it every minute, every instant, that's the number that will come out. So that's going to be a third type of interest, compounded continuously. Okay. All right. Now, so is this all right? Does that make sense, how to make those computations? You need to know this formula, the compound interest formula. Okay. Now I want to do this. Invest $1 at 100% for 1 year. Okay? Does the plan make sense? Well, I'm not saying how I'm compounding it yet, right? So just $1, 100%, 1 year. What if I just do simple interest? $2, right? That makes sense. So if I do n equals 1, n equals 2, n equals, let's say, 12, that's monthly, n equals 52, that's weekly, right? What? No, yeah, that means semi-annually, right? Semi-annually. So every 6 months, this is annually. I can do just n equals 100, just whatever, just decided to do it 100 times, okay? Then we can do it n equals 365, so that's daily. I'm going to use Excel at this point. I'm just changing one number, okay? Now see what will happen. But I'm doing the same computation, $1, 100% for 1 year. I'm just going to compound it differently. Oh, I know. Then we just have to, we don't have to go to college anymore. So I'm just going to put my values over in here. 1, 2, what did I do? 1, 2, 12, 52, 100, 365, 2, 99999, just because I can, right? Now the formula would be 1 times 1 plus, so the rate is 100%, right? So that's just 1, right, as far as the percentage goes, divided by n to the power, well, t equals 1, right? It's for 1 year, so to the power of really n in this case. So $2 as expected, right? If I just do it once at the end of the year, I'm going to end up with $2. If I do it semi-annually, I get 2 1/4. Okay, just because I computed it twice. If I do it monthly, I'm getting this much. So you see, I'm still jumping ahead. If I do it weekly, 2.69. If I do it 100 times, I'm getting this much. If I do it daily, I'm getting this much. If I do it this ridiculous amount of times, I'm getting this much. So again, what do you notice? Do you notice anything? It's slowing down, it's still increasing, right? So look, so 227711882287, right? That's where the breakage happens. So that's pretty close. So this number right there, 2.718 or so, is that magic number that came up earlier today called number E. That's E right there. That constant, 2.718. Well, it's just, oh, it will come up again. Well, you mentioned it earlier. But this is really the definition of E. It's the definition of E. Where's my writing thing? Is this. It's just 1 plus 1 over n to the power n as n goes to infinity. You want to make n as big as possible. Okay? That's E. It's one of the famous constants. So E is approximately 2.718 blah, blah, blah. Just like pi, if I say, pi, you think 3.14, right? You don't think of pi anything else than 3.14, do you? How many decimals do you remember in pi? That's it. That's all right. Because your calculator has a pi button. Well, your calculator has an E button in it too. Now, if you look at your calculator and you locate the button that has letters L and N on it, do you see a button like that on your calculator? It could be LN with an X, but the one that has the LN button. Do you see that? Right above it, it should say e to the x. So that means in order to get to that, you have to hit second. So if I ask you to compute e to the power 1, you'll have to, in your calculator, depending on the calculator, if you have a graphing calculator, you'll probably have to hit second, then ln button, and then 1, and then enter, right? What do you get? If you like one of those graphing calculators. Yeah, so you do get 2.718, blah, blah, blah. I can ask you what is e to the power 5. You'll do the same thing. So this is for, TIs, 83s, and above. What'd you get? 148.413. So E is a number. It's just a constant. You don't need to even know that it's 2.71 or whatever. Your calculator has it. This calculator in Windows has, you see, I see that LN button. So in order to get to that, this is their version of second, the inverse. So you see, if I hit that, e to the x appears. Okay, so if I do, what? Well, we'll talk about that later, but. So here we go. So that's e to the power 1 on my calculator. If I want to do e to the power 5, I'll get that. It's just a number for now. Just like pi. Pi is a number, so is e. E is just a constant. It's always equals 2.718. You'll see where it comes up. It comes up a lot when we deal with this exponential growth, the population growth, and things like that. Things that grow continuously. Okay, things that constantly change, so like population constantly changes, right? Population of bacteria, whatever. So that's where that number shows up. If you're a fan of Excel, anyone? Excel has a E function that's just exp, the exponential. So if I do exp of 1, it will tell me the number E. Okay, so that's the command in Excel for the exponential function, exp. So that automatically implies E. So E, the first person to write that number down was this guy. Have you heard that name? Yeah? Because when we start talking about great mathematicians, who comes up? Newton. Who else? Well, Einstein. He was actually a crappy mathematician. His wife was good. She did all the computations. True story. I'm not denying that. He was, I mean, by comparing his math skills with his other skills, math was substandard, which still kicked, So you got Newton, you got what? You, all right, you, and there's Gauss. There is another guy you should know, but how do you say that? No, Euler. Yes, that's German EU combination, so it's pronounced as Euler. So Euler, that's how you pronounce his name. I know that the German thing, and E is really from that he got all that. He felt that's that important, so he just gave it his first initial. So he's one of the big guys, Euler. What? I've known to put a question, how do you pronounce this name out of respect for almost multiple. You had to write Euler to get credit for that, out of respect for this guy. What? No. I mean, I'm not going to ask you to spell like isosceles or things like that. I can spell scenario, I think, but can you spell isosceles? That one is hard to spell. I don't know how to. That's okay. Really, the same scenario? Did I spell it wrong? Oh yeah, that's clearly wrong. But Euler. So this gives us the exponential function. This is the mother of them all, that really the only one that matters. F of x equals e to the x. So this is the exponential function, e to the x. It's kind of, does that fit our definition of exponential functions? Remember the definition, you have a base that's positive, e is positive, and e is bigger than 1, right? E is 2.718, so we kind of know the graph of e to the x is just, it's that. That would be the graph of e to the x. It's a little bit above graph of 2 to the x, but it's below graph of 3 to the x, right? This would be 2 to the x. This would be 3 to the x. E to the x is somewhere in the middle, because e is between 2 and 3, right? So for now, all you have to get from that e is just a constant. Your calculator has it in it. You don't have to have it memorized. It's just a constant, just like pi, just like any other number. E is irrational, by the way. It's one of those crazy decimals that goes on forever and ever and ever. Okay? Now, again, if I go to that foo plot thing, and I'll just graph 2 to the x, 3 to the x. I don't know if it will do e to the x. Oh, it did e to the x. So we see e to the x is the blue one. So 2 to the x, e to the x, 3 to the x. So it's in between. And it should make sense, right? Because e is between 2 and 3. Okay? All right. So everything we just talked about still applies to the graph. You shift it, you flip it if necessary, things like that. We will use this number later, but for example, as far as the interest goes, I don't know what happened on my pages. There is a formula, the interest compounded continuously. So this is when n is infinite, okay? We don't have a specific value of n, it just continues. So the interest being compounded always. So the formula for that, I'm not going to derive it, but it's P principal, and then E raised to the power R T. So that's the famous PERT formula. PERT. Okay? We'll use this formula to model everything that has a continuous growth or decay for that matter. If we want to model population, we'll use that formula. And it doesn't matter what deer population, human population, bacteria population, we can use that formula to model that. You happen to have a pile of uranium in your living room, we can model the amount left after thousands of years using the same formula. So your radioactive decay, carbon dating, you might have heard of that, right? If you find a bone in the woods, you can figure out how old it is. Same formula. So everything that changes continuously, where again, P is the principal, R is the rate, T is the time. So if I use the same scenario, and I'll try my best to spell that one. Is that correct? Scenario, is that better? Yes? Okay. So again, we're going to invest $1,000 for 10 years at 3.5 interest rate, but only compounded continuously. It'll be 1,000 e to the power 0.035 times 10. Okay, so if I use the calculator to compute that, so it's 0.0, I already did that, so 0.35 e to raise to that power times 1,000, so yeah. So that's as high as it gets. Just by messing with the number of times you compound interest. This is as high as it can go. Okay? It won't go any higher than that. If you want to make more money, put more money down or find a better interest. Or more years. But just by changing the number of times interest compounded, this is as high as it gets. Okay? Now, just because we can, I will give you arguably the most beautiful identity. How do you spell beautiful? Yeah, how do you spell that? That's what I had. Then what? Identity. In all of mathematics. You should. It won't be on a test. Don't worry about it. But it's just a cute thing. Actually, it's called Euler's identity. Okay? So, I'm going to take number E. Now, what do we know about E so far? It's irrational. It's just one of the, nasty numbers. Decimal goes on forever, never, never. And then I'm going to take another one of those numbers that's irrational that we all know and love. What am I talking about? Pi. I'm going to put pi as an exponent on top of E. Then I'm going to take another number that we have learned this semester that's not quite a number. What am I talking about? I am going to take it times I in the exponent. Okay? And then I'm going to add the first number probably ever used in human history. What do you think that was? 1. I'm going to add 1 to that whole thing. Okay? And to make this thing absolutely awesome, what do you think that whole thing should equal to? What would be completely like, what? 0. That's right. That's true identity. E to the power I pi plus 1 equals 0. Which is just spooky if you think about this. Well, it's an imaginary number. We get it as solutions to our equations. Now, I don't know if my if this calculator will handle this. Because I've seen this. Have you guys? It hadn't happened in this class. This calculator completely sucks. Because look, if I do 0 to the power 0, this calculator tells me it's 1. It should be undefined. So this calculator is broken to begin with. So I'm not sure how. I won't be able to check it on this calculator, I don't think. But on some of your fancier calculators, this is a true identity. This is amazing that it works like that. It's very surprising. It should be. Did it work? There should be an I button on your calculator. It's all right. You can plug I into your polynomials. I times pi is I times pi. Well, it makes it work like that. I mean, in order for you to appreciate where all that came from and to show why that's true, you have to stick with me for a few more years. If you end up taking Calc 2 at some point, Calc 2, we'll be able, after taking Calc 2, to show why that's the case. Okay? It's not, but for now, we just, this is like looking at the beautiful sunset at this point. I mean, look at this. This is completely amazing that just happened. Because you don't expect that to happen. Do you agree with that? This is like, looks very random. You have irrational number, not even a number, and then plus 1, which we all know and love, and collapses to 0. Which is quite cool. So am I going to see you all in Calc 2 now? Or did I tickle your curiosity bone with that one? Are you going to... You have to go through pre-calc and Calc 1 and then Calc 2 in the spring. Which you can... Yeah, because look, if you take pre-calc in the spring, this is fall, right? All right, you take pre-calc in the spring, you come back, take Calc 1 in the fall, and then we'll teach Calc 2 in the spring. Well, whatever you're moving, I'm sure they'll be teaching Calc 2 somewhere. And if whoever's your professor, you're like, hey, I had this crazy math teacher who wrote that on the board and said I might need a little bit of Calc 2. Now, again, Calc 2 won't deal with I at all, but at least it will give you some formulas that you'll be able to justify that, which is quite awesome. Well, he came up with the general form. He came up with any number to the power. Basically, he came up with this function. So you have, well, let's just call it that. And there's a way to define it, but it just happened if you plug pi instead of a, you'll get -1. E to the pi equals -1. So add 1, you get 0. Quite cool. All right, good. I'll stop on this optimistic note. And so yeah, that was